So welcome back. A few things before starting. First off is about Orion. Even though I'm not assigning it officially, it does keep track of whether you've worked on the questions there. So I mean, that's, for me, that's, well, for I hope all of us, that's good news in the sense that if you answer on average 20 Orion questions per chapter, and we'll get through certainly through chapter 8 and hopefully deep into chapter 9 by the end of the semester. If you average 20 questions or more on Orion, I'll give you the full credit for the participation part of the class, the 10%. I just want you to keep trying to answer questions. I wish they were more perfect questions. I'm eventually going to have to bite the bullet and have them send me the entire collection of questions and edit and or rewrite them all, which is a horrifying thought. But, you know, got to do what you got to do. So that's Orion. And the other thing is the fourth problem set, because of how the material's falling here, I've made it due on Monday, a week from, well, you know, not a week from, you know, 7 days, 5 days from now, whatever. It covers material that we'll deal with, we've dealt with already in rockets, but also in balloons and in water distribution. So my hope is that my plan is that by the end of class on Friday, you'll be able to answer all the questions. I've put that problem set on UVA Colab because I wanted to seize control of the whole thing again. So now I've got the questions there written by me with my answers as opposed to other people's questions and answers. You should be able to look at it many times, but you only can submit it once. So you can already answer some of the questions. Some of the other ones are sort of in our future, at least in class. And 10 questions. Any questions about the logistical stuff? All right. So balloons. The story of, well, up until now, we've talked about solid objects experiencing forces, undergoing acceleration as a result, various types of forces, gravity, support forces, maybe elastic forces associated with springs and things like springs. And now we're going to go into things that are not solid, namely gases and liquids, which collectively are known as fluids. So fluid is a general term, catch-all, for things that don't have a fixed shape. And you can't push on a fluid quite the same way you can push on a wagon. When you push on a fluid, like I'm doing right now, it's not by way so much of a force, although you do use forces, but it turns out that pressure is often a better way to describe how you interact with fluids and cause them to accelerate. They have mass and they undergo acceleration, but the way you push on them often is more complicated because you sort of can't grab hold of them. And so that's part of the story of balloons, and balloons is a good example of an object. I'm thinking in particular balloons that float in the air, that rise up in the air. You know, what's pushing them up? It's not, you know, you can sum it together as a force, but it involves a lot of things associated with pressure. Okay, so the first question related to this, in a sense, is a helium balloon has mass, and helium is stuff. It has a mass, and yet you know from experience, helium balloons, properly inflated and stuff, they don't fall to the floor, they float to the ceiling. And so the question is there a real force pushing up on a helium balloon? You okay with the question? How many think yes, there's a real force pushing up in the balloon? How many think no, there's no force pushing up in the balloon? Okay, the majority are going for no force pushing up on a balloon. Just to pursue this a little bit, to measure its mass, you would shake it, right? And how does it accelerate? To measure its weight, you would put it on a scale. I guess, that's a little bit troublesome. You have to tie it to the scale. It would read a negative number. But what are you actually doing? Just to get ahead of ourselves a little bit, I'll tell you that there actually is a force pushing up on the helium balloon. And I've told you all along that if there's a force acting on something, it's being exerted by another thing. What do you think is... So first off, there is a force acting on the balloon, the helium balloon. It's an upward force. What do you think is exerting it? It is a difference of densities issue. And what's the density of what? The air. It's the surrounding air. Yes, and as we'll see, it's a difference in densities between the two objects. The helium balloon, it turns out, is less dense. And density is the thing we have to define too. Density is the measure of how much mass there is per portion of volume, per unit of volume. So it's mass like kilograms, and volume is measured in, well, cubic meters is the metric unit of volume. But a thousandth of a cubic meter is familiar to you as a liter. So kilograms per liter is how much density there is. And air is not very dense. Its density, it actually has only 1.25 kilograms per cubic meter, which is this big. It's a big box. That's 1.25 kilograms. But it's not nothing. And if you tried to shake it, it's not trivial. It's there. And it has weight. And it also pushes up on things immersed in it. And so part of the story for today is to explain to you why an object immersed in it, like a helium balloon, plopped in the middle of this air, gets pushed up by the air. All right? It's real. It's a real upward force. You're experiencing it right now. It's not enough to do much for you, but it slightly reduces the value you read when you stand on a scale. And when it reads your weight, it's actually a little under measuring. It's reporting a little light because you're not truly free of other forces apart from gravity alone. You're actually being pushed up a little bit by the surrounding air. That force has a name. It's called the Buoyant Force. And it's one of the reasons why, up until now, I keep saying in questions stuff like neglecting effects due to the air. Well, one of the effects was air resistance, and we sort of ran into that early on with falling objects. But the other effect I was sweeping under the rug is the buoyant effect of being in the midst of all this air. Okay? So that's a preview of where we're going a little bit here and there. So about balloons, they are held taut by the gases inside them. So when you blow up a balloon, you're stretching this thing. Getting that balloon to not have its favorite, its equilibrium shape is this, right? It wants to be like that, and I'm stretching it. Well, I'm not stretching it with my hands with forces. I'm pushing it outward with the gas inside, which, well, yeah, it's exerting forces, but they're all over the place. And a better way, it turns out, of describing those outward forces is going to be pressure. So I put air inside, creating pressure inside, which pushes out and stretches the balloon. Some balloons float and others don't. So, well, it's fun in cartoons to have somebody blow up a balloon, right, and they float off, woo, off they go, right? Never happens. Yeah, because you can't make the right sound effects. Air itself, an air-filled balloon immersed in air simply doesn't have enough of an upward buoyant force to support itself, and actually it falls to the ground, as you certainly noticed. On the other hand, if you blow up the balloon in something that's very dense, there's a lot of mass per liter, and also therefore a lot of weight per liter, like water. Well, even an air-filled balloon will float in water, but it won't float in air. So to get balloons to float in air, you've got to work hard at it. And there are two easy solutions. One of them is hot air, and we'll see why hot air floats in ordinary air, and helium. We'll see why helium floats in ordinary air. All right, so that's part of our story here. My various questions that we'll go after. So the first one is how does air inflate a rubber balloon? So the first step of me blowing up a balloon, what happened? Why does it stretch the balloon? And the answer is, as I sort of already said, that the pressure of the air that I put inside the balloon pushes the balloon's skin outward. So it's air pressure inside the balloon that's stretching the balloon. Background on this, air is a gas, so that is a particular type of fluid. It's a fluid consisting of individual atoms and molecules. So that statement is based on hundreds of years of science and people trying to figure out what's going on here. When all the dust settled and people figure out really what's going on, it turns out that this stuff that we're immersed in consists of lots of tiny little particles, a few of which, a small fraction of which are truly atoms. That is, individual, these simple systems that consist of an atomic nucleus. I mean, you've encountered this in somewhere in your earlier schooling. There's a little nucleus that is surrounded by a cloud of electrons. The exact nature of that nuclear nugget and electron cloud is complicated and not really part of the story for today. But an individual atom, there are some, and they travel around as this little object, and they're independent of one another in the sense that they spend very little time in contact with any other atoms or particles like atoms. So they're just bouncing around. Okay, we'll come back to that, the bouncing around business. Those were atoms. The atoms that I have in mind are, well, among other things, helium, although helium is relatively rare in this room. There are other atoms. The most common atom that's in this room is argon, one of the noble gases. We used to have a periodic chart up there, and I could point out the parts. But the rightmost column of the periodic chart are what are known as the noble gases. They are atoms that are so non-reactive, that they're so unlikely to stick to any other atom with chemical forces that they pretty much stay aloof and look after themselves. And the lightest of those is helium. The next one is neon, which is also present in this room, but not so common. Argon's the most common. Probably neon's next. And then the larger ones that are more exotic, krypton and xenon. And those are around, but they're tiny fractions of what's in this room. So those are the atoms, but most of the particles in this room are not atoms, they're molecules. And molecules are atoms that have stuck to each other with chemical forces. And we'll talk a little bit about that when we get to talking about how a wood stove works. The wood stove, you're burning chemicals to form other chemicals. Some of those chemicals are gaseous and some before and after, and so I'll talk about the whole process of sticking atoms and molecules together with chemical bonds. But that's for the future too. So by far the most abundant particles in the air in front of us are nitrogen molecules. Nitrogen molecules consist of two nitrogen atoms, these little, when I'm hesitating to call them as planetary systems, because the idea of planetary sweeps under the rug so much of the structure of an atom. They're only very slightly like a planetary system. Quantum mechanics makes them much more intricate than that, or just different. And so the point is, a nitrogen atom has this nuclear nugget with electrons around it, and by itself, it's an atom, yeah, but it doesn't stay by itself very long. It almost immediately pairs up with another nitrogen atom to form a structure that now is pretty much chemically inert. And so nitrogen in our atmosphere is pushing, it's not quite 80% of our atmosphere. So what's between us right now is overwhelmingly nitrogen molecules. Nitrogen atoms are very rare. I mean, I guess like someday I'll figure out how many there are in this room, but it's going to be not quite a handful, but on that order. They're exquisitely rare. This is one of the reasons, those of you who have paid attention to sort of biology and stuff, one of the limiting factors on plants and animals is being able to get hold of nitrogen to work with, because nitrogen is an important part of all living things. It's part of DNA, for example. And getting nitrogen to work with is tricky because the nitrogen in the air is really hard to break apart and get into useful form. Nitrogen atoms are just, nitrogen molecules are really stable, really hard to disassemble and then get a nitrogen atom to work with. So nitrogen fixing their plants and bacteria and stuff are crucial to life. So that's the story of nitrogen. Oxygen, to an extent, the same story. Now, oxygen atoms by themselves don't stay that way very long. They stick together as pairs. You end up with oxygen, two molecules, two oxygen atoms together forming an oxygen molecule. And something like 20% of the particles between us right now are oxygen molecules. And there's a little bit of a smattering of carbon dioxide, more on that when we talk about climate and climate change. What else is in the air? Water. Most of the time, you all have probably studied the content of the air somewhere along the line. It was 79% nitrogen, 19 or 20% oxygen, and that's dry air. They leave out the water. But in fact, water is present in the air, and it's a significant fraction of the air, and it depends on the relative humidity, that whole story, something that we'll also talk about in 2 weeks or something like that. On a humid day, several percent of the particles between us will be water molecules. All right? So long harangue about the particles. These particles are bouncing around, and they're bouncing around frenetically. I'm just wanting to plan ahead. Yeah, I'm going to go to this slide here. They're bouncing around frenetically with what? Well, to bounce around, to move, they have to carry with them, well, two conserved quantities, momentum and energy. The fact that they're in motion means that they've got a velocity, they're carrying momentum in the direction of their velocity. They have a very tiny mass. Their velocity, it turns out, is quite large. But when you multiply those together, tiny mass times big velocity, pretty big velocity, it's still a tiny little dose of momentum in the direction they're traveling. So thing to keep in mind is all these little particles carry a little dose of momentum in whatever direction they're going. How about energy? Well, they do. They carry energy too, because energy is related to speed squared. Technically, it's the mass of the particle. It's half the mass of the particle times its speed squared. That's how much energy it carries in kinetic form. And so that each of these particles carries a little kinetic energy. They bounce off each other and off of everything they encounter. And when they do that, when they make that bounce, unlike ordinary balls, they bounce, typically they bounce perfectly, in the sense that when they hit something that's immovable, so that they don't transfer energy to it by doing work on it, whatever energy then they had when they go in, they come out with. They don't squander some of it. Okay, so they bounce perfectly. Real balls can't bounce perfectly because they got too many particles. They're too complicated. Atoms and molecules have the possibility of bouncing perfectly because they're so simple. Not all of them are so simple, and when they get to be complicated molecules and stuff, they have ways in which they can transform their energy from one activity to another. But the main point is they mostly just sit there bouncing forever. And what keeps them moving at all, what keeps them moving is thermal energy. And we've talked about thermal energy. I've ranted about thermal energy in the past as sort of the waste heap, the garbage dump of ordinary energy. It consists of ordinary energy, but it's chopped up into little bitties and sprinkled randomly or statistically among all the particles. And here's an example of that. When you've got a container filled with a gas, like this is a tire filled with air, and in an animation they would all be moving. And online, in the online book, I've started to animate these guys. So they're all moving around frantically. What's making them move is that they have thermal energy. The gas as a whole has thermal energy, which means it has a certain amount of energy to start with that was chopped up in little bitties and distributed statistically among all the particles. So here it is. It's in their motions. The vast majority of the thermal energy is literally in the kinetic energy, the motion of the particles. When they hit each other, that energy can get briefly stored. During the impact, they bounce off each other. There really is a whole bounce process. And so during that bounce, the particles are dented a little bit, and then they push apart. And they might even come to a stop, or pretty close. And during that time, the energy is momentarily in the form of a potential energy within these dented particles, atoms and molecules. But mostly it's in the kinetic form. And as we'll see, the temperature of a gas is proportional to the average thermal kinetic energy of the particles. So what average means take all the particles, don't concentrate on one. Thermal energy, that means take only the energy that's associated with this chopped up, distributed energy, not the energy of the system as a whole. So if you take this tire and you throw it across the room, all of the atoms and molecules in the gas inside are traveling, they're moving across the room as a group. That part of the kinetic energy doesn't count. Only the part where you stop the tire and look at it without worrying about the overall sort of center of mass motion, the collective motion. Get rid of that. Look at the motion of each one looking after itself. That's the thermal energy. Average thermal kinetic energy per particle. Well, sum it up over all the particles and divide by how many particles you got. That average thermal kinetic energy per particle will give you a value. It'll be some amount. It's not very much, but it's a tiny amount per particle. That is going to correspond to the temperature of the material. And we'll deal more with temperature in the future, but temperature, so I'll flesh this out a little bit for now anyway. The temperature scales you're used to, probably most of you are most comfortable with Fahrenheit, right? Where the 0 of Fahrenheit is freezing. That's not true. The 0 of Fahrenheit is nothing interesting at all. It's 32 is freezing. Yeah, the 0 of Fahrenheit is a weird. It has a meaning, but it involves mixing salt with ice and playing around with it. Forget it. But it's a scale in which 0 is some particular value, and you can go below 0. And on rare occasions in Charlottesville, it does. Okay? The other temperature scale that many of you are familiar with is Celsius, where 0 now means something special. 0 is the freezing point of water, melting point of ice. Okay? But you can go below 0. The temperature scales that are useful when you talk about the average thermal kinetic energy per particle, and that being proportional to temperature. The temperature scales you want to do that are ones in which the 0 corresponds to the particles having no remaining thermal energy. They just can't move. All right? And that 0 is really cold. A scale in which 0 corresponds to no thermal energy is really cold. It's called absolute 0. And on the Fahrenheit scale, it's minus 459, I believe, degrees. On the Celsius scale, it's minus 273. So these are really cold temperatures. But that's the real 0 of temperature. And on a scale in which 0 is set to be absolute 0, the gas particles come to a stop when you get to that temperature in principle. All right? So, anything more I want to say about this? We'll work eventually in a scale in which the 0 is defined as the real 0, this absolute 0, and it has spacing between temperature steps the same as Celsius. So 1 degree Celsius increase in temperature is going to be the same as the 1 unit increase in this temperature scale. That temperature scale where 0 is absolute 0 is called Kelvin. The word degree doesn't show up, so it's 0 Kelvin is absolute 0. And 1 degree, you mean it makes it up. 1 Kelvin, no degree. 1 Kelvin is sort of one increment, 1 Celsius unit increment in temperature. And to get up to room temperature, then you have to get up to about, we're in an environment that's about 300 Kelvin. So it's pretty, so it's big on numbers, but it doesn't feel all that hot in here yet. Okay? Takeaways from this are what? Having ranted about this forever. The particles in a gas are in frantic motion because they have thermal energy associated with the local temperature. And the local temperature here, as I've said, is about 300 Kelvin, or you can call it 70-ish degrees Fahrenheit, or about 20 degrees Celsius. Okay? At those temperatures, all named differently, same temperature, the speed of the particles is really fast. How fast? Well, like about half a kilometer per second. The average particle in the air right here is traveling half a kilometer per second, which is startlingly fast. It doesn't make much progress because it hits things so often. So if you would watch it, it would be bouncing off stuff billions of times per second. And so it makes very little progress. But that's the action. It's all driven by thermal energy. If you get rid of the thermal energy, everything just settles to the... Everything would settle at the bottom of the tire, my picture here, and not be moving. Okay? Well, how do you deal with all this bouncing stuff? Well, you're never in a situation to watch an individual air particle do anything. You're looking at their collective behavior as a group. As a group, they have a certain amount of thermal energy. As a group, they impact whatever is immersed in them. For example, the walls of that tire or the surfaces of a balloon. They are hitting the surface of this balloon from the inside all the time. Pepper, pepper, pepper. And every time they do, and I'm sort of try to animate this in real life, it's like a whole bunch of balls bouncing against. I anticipated that problem. I was going to not use the wall because I would do it in the first bounce. I would lose them all. I have more, right? They're all bouncing. Every time one of these balls hits the table, doing it vertically helps because the balls keep... Gravity is helping us bring them back together, but gravity isn't an important part of this story. The main thing is that every time one of these bouncing particles hits the surface, immersed in it, it does a bounce, right? And we saw with bounces that when you bounce off something, you give it all of your momentum and even more because you end up going backwards. So these balls, when they're hitting, just take one. Every time that thing hits, it gives all of its, in this case, downward momentum to the table, and even more, because it ends up with upward momentum. And then it bounces again, and bounces again. So if you have a countless number of these particles all hitting the wall of, well, a balloon, let's let it be the wall of this room. So this room is a giant balloon now, and all the air particles are hitting that wall. And every time they do, they transfer some momentum to it. And these transfers of momentum divided by the time over which that acts is the force. Right? A momentum transfer is a force times time. Well, if you divide by time, you get the momentum transfer per time is the force. So if you have lots of these, a certain number of impacts per second, transferring a certain amount of momentum per second, well, that's the force being applied to the surface. And it's a big force. There are a lot of them hitting there, that side of this room, every second, and they transfer a lot of momentum to it. How much? Well, it depends on how big the room is, which is awkward because you'd like to be able to characterize it not in terms of how large this room is, and you have to go over there with a ruler and measure, but rather with some characteristic of the air itself. And so this air that we're breathing right now is exerting a certain amount of force on the wall of this room. And to characterize this air, you don't really want to have to care how big the room is. So what you do, you divide by how much surface area the room has. How much, in effect, you're looking for how much force is exerted on that wall by the air. Divide how much force is exerted on each unit of surface area of that wall. Bottom line, take the force, divide it by the surface area, so that you now have the force per unit of surface area. That characterizes the air, not the wall. I hope that makes some sense. It's not my most lucid delivery. So, if you take the force exerted by a gas pick a surface and divide by the area of that surface, you get what's known as pressure. And that's where I'm heading. Pressure is the force per unit of surface area exerted on something by a fluid. So this air that we're breathing right now pushes plenty hard on any surface, astonishingly hard. How hard? It exerts 100,000 newtons per square meter. It's an approximate value. It's I think a little bit more. Depends on the weather. It varies a little bit. Barometric pressure, it matters. Okay? So a unit of surface area that's 1 square meter. It's about like this. Okay? The force exerted on that is 100,000 newtons. Remember, Newton is about the force exerted, the weight of a small apple. So 100,000 newtons is like the weight of a city bus. So huge force on every square meter. That wall is experiencing, because every square meter experiences 100,000 newtons, and there are a lot of square meters there, it's a fantastic amount of force. Is that okay with everybody? I mean, you can take my word for it. I'll show you in a minute that the force is really there. You might wonder then, so why this has a surface area of, I don't know, 1/10 of a square meter, something like that. Why isn't it's experiencing a huge force, why doesn't it accelerate like crazy? It's got almost no mass. That kind of force pushing on this front surface would make this accelerate fantastically. The reason it doesn't accelerate is because this side's experiencing such a force, but so is this side. And they balance essentially perfectly. And I'm using the word essentially because the little details do matter, like how you orient it. They're there's a little imperfect in some of these pushes. But there's a huge force from this side and a huge force from this side. They sum pretty much to 0. And that's the case for you all. You're experiencing forces on your front, on your back. Every part of you is being pushed inward by the surrounding air with using pressure. So there's a force of about 100,000 newtons on every square meter of you, pushing you in here. You don't really notice this because squishing stuff doesn't have a big effect on you directly. The uniform pressure pushing in doesn't have much of an effect. It does have an effect on the parts of you that are not solids or liquids, the gaseous parts of you, which are, for example, in your lungs. The air inside your lungs does experience this inward push, but fortunately it pushes outward just about as hard, and therefore pretty much cancels that out. All right. At this point then, let me show you that inward push, that push on surfaces is real, and the classic way to do this is with these, they're called Magdeburg Hemispheres. These are little ones. The original demonstration done a couple hundred years ago involved big ones. And the idea is this. These are 2 halves of a hollow sphere. When I put them together, they seal. There's a rubber gasket, O-ring in between, that seals the environment inside. And through this opening here at the top, we can remove the air that's in there. So we'll have a sphere of two halves with nothing inside. In that case, I should say, first, at present, when I just put them together, the air on the outside is pushing inward with this tremendous inward pressure, and therefore a lot of force inward on this round surface. Similarly, there's a lot of force this way on the other surface. Why are these easy to bring apart and stuff? It's because the air inside is pushing out and compensating, in fact, pretty much canceling the inward force on the outside. So you have an inward force on the outside of this pair of hemispheres, and you have an outward force inside. They pretty much balance, nothing happens. Is that okay? If we take the air out from within the 2 halves, there is no longer anything pushing out. The air really does vanish, and the consequences are that the inward forces on the outside, due to the air and its thermal motion, they win. They dominate, nothing's pushing out. And those forces are big. And I'll take the air out first. Let me make sure all the plumbing's set up right. Okay. So I'm going to use a machine to remove the air. Is this set up right? Yeah, it's sucking. All right, come on. I've got to find there's a rotary valve here that I have to. I think that's, yeah. Okay. So I'm now taking the air out. I'm not sure why that gauge is not reading anything. Okay. So I've taken the air out. I'm not actually attracting the air out what's happening is the air molecules are bouncing around. Occasionally they find their way into this pipe and out into this pipe, and that machine down there makes sure they don't come back. Once they go that way, they can't return. So we have to wait for them to choose statistically to come out. And when they do that, they're gone forever. Now I'll seal the valve, turn off the pump. Okay, now I understand how that feels. 2 volunteers to try to pull this apart. Okay, Daniela, you can twist the arm of one of your friends to pull the other half. Okay, Patty, come on over. Okay, thanks. And this is just doable, but it would take the strongest people in the room to get it apart. You should not be able to get it apart. Okay, this is done. Okay, I'm going to let the air in. So be careful. When you let the air back in to push out and balance, that's all it takes. Thank you, guys. Yay. So the point is, the air around us is really pushing hard on everything. It doesn't. You don't notice it because, in fact, we're incompressible. The inward forces on us don't change us very much. If what's in our lungs matters, that's another part of the story. But basically, you don't notice. It's like when you step on a coin, it doesn't get smaller. It actually has pressure, and the pressure increases dramatically, but it's unable to get any smaller, at least measurably so, not by ordinary people. And the same is true of us. We put pressure on us, and not much is visibly different. So this is taking air out of the inside of a container, watching the pressure push inward on them. How about the reverse? What if we take the pressure away from something that has air inside? So here is a balloon with a trapped amount of air inside it. No choice, it can't change. I tied it off. And I'll put the balloon inside this device, which is a vacuum chamber. And I can remove the air from inside this chamber and therefore have no air outside the balloon. It's the reverse of the hemisphere thing. The result is the air inside the balloon will be pushing out. Nothing will be pushing in. And what do you think will happen to the balloon? It's going to get bigger and bigger until it pops. So I'm not adding air to the balloon. I'm simply taking away the pressure outside the balloon that's pushing in. And it can take it for a little while. And boy, it's holding on longer than I expected. Woo! Finally, okay. Yeah. Well, that's the straightforward version. This is the more fun version. Okay. Jumbo. Ooh. All right. So what's a marshmallow? Well, marshmallow is pretty much little bubbles, sugar bubbles with air inside. And this there's a lot of air inside the marshmallow, trapped sort of permanently by this sugar syrupy thing. Okay, so there's Marshmallow Man. And Marshmallow Man was banned from the Olympics for doping. And here goes Marshmallow Man. I'm taking the air out from around the bubbles. And again, they have trapped air inside, and each bubble, therefore, is no longer being pushed inward. It's only pushing outward. And so Marshmallow Man is bulking up, but it's all ill-gotten gains. As the bubbles get big enough, and they started, jumbo marshmallows, when the bubbles get big enough, they burst. but the bursting is a little less visible here. He's beginning to lose air molecules. And it's most noticeable when he stops swelling. And he's about there now. So he's starting to shrink a little bit, but because of, I could have zoomed in on this, I forgot. But anyway, he's beginning to lose air molecules through the burst bubbles. And once they're gone, they're gone. When I reintroduce air into this chamber, what do you think is going to happen to Marshmallow Man? All right. Turn off the pump. Ready? He's just a shadow of his former self. Yeah. You can. I should let you guys see up closer. There's Marshmallow Man. Total disaster. Any questions about why that happened? I mean, you know, they still taste like marshmallows, but it's it lost the fluff. Okay? So, where are we on this story here? Pressure imbalances. Basically, what I've been showing you are these ideas of pressure imbalances. That when you have simply a sheet of paper burst in the air and the pressure is the same on one side as the other, there are forces, and they're huge potentially, but they cancel each other, and so nothing happens. But if you have unbalanced pressure, higher pressure on one side than on another, those forces no longer cancel, and you get measurable, noticeable forces. Things accelerate, stuff gets pushed around. Marshmallow Man, at his when he was puffed up, when we let air in, suddenly there was a horrible pressure imbalance between high pressure outside, that is the rushing air coming in from the room, and almost no pressure inside, and therefore his bubbles got smashed, and with it him. The hemispheres had a pressure imbalance between almost no pressure inside and high pressure outside, made it very hard to pull those spheres apart. Big inward push. Okay? Pressure imbalances act on surfaces. They also act on the air itself. So if you have high pressure on one side of a room, say, and low pressure on another side of the room, and let things happen, the air itself will accelerate in response to this imbalance in pressure. And we'll see when I talk about water distribution, this is what pushes water through our pipes, is differences in pressure. Water accelerating from high pressure to low pressure. Gravity plays a role in this too, because it also exerts forces on fluids. But depending on what the story exactly is, gravity may be important, it may not be important. In these stories I just showed you, gravity wasn't an important player in the pressure imbalances. Okay. The atmosphere itself, the story of the atmosphere itself. So where did this pressure come from? And the pressure around us right now, where did it come from? And the answer to that is that if there were no thermal energy in the Earth's atmosphere, it really would all be settled on the surface of the Earth as basically a solid, or arguably a liquid. It would be collapsed on the surface, and there wouldn't be no gas involved in it. It would just be settled there on the ground. What keeps it above the ground? Thermal energy. This frenetic motion of the particles bouncing off each other causes them to push on stuff. And they can push not only on objects immersed in them, or that are encased in, but they can push on themselves. A gas can push on a gas. And so it turns out that the air down here, with its thermal energy and therefore its frenetic motion, is pushing up on the air above it and keeping that air up there. So the air down here creates this enormous pressure, pushes on the walls, it pushes on you and I, you and me, and it also pushes on the air up there. Even though there's not a surface here to sort of demarcate the transition, the air down here is pushing on the air up there and keeping it up there. Don't come down here, right? If you come down, you smush me. I hold you up, okay? And the air up there, if I could stand up there, would be pushing on the air above it, which would be pushing on the air above it, and above it, and above it, and above it, all the way to the top of the atmosphere. Thank you. Yes. Can I remember? No. Thank you. Okay. So The air down here is supporting the air above it, which is supporting the air above it, which is supporting the air above it. And the result is that the atmosphere develops a structure. It turns out that the denser the air is, which is to say the more air particles there are packed into a little region, the higher the pressure. If you keep everything else constant, more air molecules leads to more pressure. Why? Because if you've got twice as many air particles in a box, say, they hit the walls twice as often because there are more of them. They push twice as hard. So if all you do is double the number of air particles in a box, you will almost exactly double the pressure in the box. Is that okay? Hopefully that's just nearly obvious. So for the particles down here to support the particles up here, they have to push hard enough to support all that weight. They need to be pretty densely packed. There have to be a lot of them per box. But if you go higher up in the stack, so imagine a stack of boxes. The box way up high doesn't need as many air particles in it to support the weight of the air above that because there isn't much air up there. The deeper you get into the stack, the more particles you have to have per box in order to build the pressure you need to support the boxes above. Because this air down here is supporting not only this portion in my hands, but the portion above it. And the portion above it all the way to the top of the atmosphere. It has to support a column of air that is miles thick. There's a roof on this building, but ignore the roof. Just imagine it keeps on going. The air down here has to push up so hard, it holds up the weight of the entire stack above it. But the air at cruising altitude in an airplane doesn't have to be as densely packed because it doesn't have to support as much weight overhead. The column above it is shorter and fluffier. So the atmosphere has this structure in part determined by gravity itself, by the weight of the air. The structure is high density, high pressure down here. Density, if you recall I mentioned earlier, is mass per volume. So kilograms per liter. You have to have high density air here. A lot of 1 1/4 kilograms per cubic meter. That's this air down here. But as you work your way up in the stack, the density is less particles per box, because you don't need as many. The pressure correspondingly is less, because it doesn't need to support as much weight. And so density and pressure both fall off with altitude. You okay with that? This is familiar from your experience. When you go into the mountains on a car, you drive up quick, you feel your ears popping, right? Why? It's because trapped within your ear is air at the density down here. And when you go up to great altitude, I should say, the density is less, the pressure is less. Suddenly you have a pressure imbalance in your ear between high pressure, high density in your ear trapped and the now less dense, lower pressure air outside. Because you're in the mountains, there's not as much air overhead to support. Familiar? I hope that's familiar to you guys. You get this in an airplane too. The airplane, they don't let you go up to the full altitude of the airplane inside. If they did, you would all pass out. They take it up to about 8,000 feet of effective altitude, and after that they stop. They trap the air and prevent it from leaving, so that the pressure inside the plane is actually much higher than the pressure outside at 30-odd thousand feet. The good news then is you have enough density of air, enough air molecules per box to breathe and be comfortable. The harder news is there's a big pressure imbalance between high pressure inside the airplane and low pressure outside. That's why the airplanes have to be very strong. They're bottling up this air, and they are therefore under a lot of tension, trying to pop the bottle. All right, let me tell you where we're going before you. If we start playing with, we put air in air, it will turn out, first off, that the surrounding air will exert a force on the air and the portion of air immersed in it to hold it up, to support its weight. And if you replace that air with stuff that's lighter and fluffier than the surrounding air, the upward support acting on that portion of now different gas will be upward and exceeding, be more than the weight of the material you put in there. So a helium gas, helium-filled balloon, or a hot air balloon, both of them way less than the force exerted up on them by the surrounding air, and they will float and actually accelerate upward. And we'll do that on Friday.